Hey everyone, welcome back. Today we're diving into some theoretical physics stuff.
Oh, yeah.
We're going to be looking at chapter 47 from Pasted Text.
Okay.
And this
Yeah,
chapter
yeah.
is making some pretty big claims about solving some big mysteries in physics.
Yeah, it's
It's pretty interesting.
yeah, so let's jump in.
Sounds good.
What are they saying here?
Well, they introduced this new potential framework
Okay.
called SMF RVS dynamics, which stands for subtle magnetic fields and relative vacuum of space.
SMF and RVS.
Exactly.
Got it.
So basically, they're proposing that these subtle magnetic fields, or SMFs, are shaping the vacuum of space.
Okay.
They create these things called pressure gradients in the relative vacuum of space, or RVS.
Pressure gradients.
Yeah, and get this, they claim that these gradients could explain like a whole bunch of phenomena,
Like what?
from gravity to dark energy, even the nature of time itself.
Hold on. So they're saying that empty space
Right.
isn't really empty.
Exactly.
It's like this dynamic medium shaped by magnetic fields.
Yeah, that's the basic idea.
Wow. Okay, that's pretty different from how I usually think about the universe.
It is a pretty big shift.
But are they just like
Later.
throwing out these wild ideas, or are they actually like trying to solve specific problems with this framework?
No, they are definitely trying to solve specific problems.
Okay.
And they start with the big one, quantum gravity.
Right.
I'm sure you're familiar with the whole challenge of reconciling quantum mechanics with general relativity.
Yeah, like trying to fit a square peg in a round hole.
Exactly. And this chapter is arguing that SMF RVS dynamics could bridge that gap.
Interesting.
They suggest that gravity isn't a fundamental force that needs to be quantized, but rather emerges from how those subtle magnetic fields shape the vacuum.
Okay, so instead of gravity being like
Yeah.
a separate force, we're saying it's more of a side effect of the vacuum structure.
Yeah, like a consequence
If
of...
I'm trying to picture this.
Well, they use this interesting analogy.
Yeah.
They say to imagine space-time as like this vast ocean,
Okay.
and the subtle magnetic fields are like the currents and ripples in that ocean.
I see.
And those ripples and currents are what we experience as gravity.
Okay, I can kind of see that.
Yeah.
So objects aren't attracting each other directly, they're just responding to the shape of the vacuum around them.
That's the idea. And this approach, it actually simplifies things.
Oh, so?
Well, because you no longer have to try and force those two theories, quantum mechanics and general relativity, together. They
Right.
just become different aspects of the same underlying process,
Which is?
the dynamics of the vacuum.
Okay, so we got this vacuum-driven gravity concept.
Right.
But what about dark energy?
Ah, yes, dark energy.
The universe is expanding faster and
Yeah.
faster, and we don't even know what's causing it.
And the standard model usually needs this thing called dark energy to explain this,
Right.
but no one really knows what dark energy is.
So does this new framework have an answer
It does.
for dark energy?
Yes, and it goes back to those vacuum pressure gradients.
Oh, okay.
Instead of needing this mysterious dark energy,
Yeah.
SMF RVS dynamics suggests that the accelerated expansion is caused by the vacuum itself.
So they're saying the universe is, what, like self-inflating?
Pretty much. Like it's got this built-in engine powered by the vacuum.
That's pretty wild.
Think of it like a balloon.
Okay.
Instead of needing some outside force to inflate it, what if the air inside was pushing outwards?
I see.
That's kind of what they're suggesting.
That actually makes a lot of sense.
It's definitely more intuitive.
Than dark energy.
For sure.
So we've got gravity and dark energy potentially explained by this dynamic vacuum.
Hmm.
What else does this framework tackle?
Well, they also talk about black holes.
Oh, yeah, black hole.
These incredibly dense objects where gravity is so strong that nothing can escape.
Right, but I thought those were like
Yeah.
bottomless pits that just gobble up information and no one knows what happens to it.
Well, that's the traditional view. But SMF RVS dynamics suggests something different.
What's that?
They propose that black holes aren't points of singularity, but are actually incredibly dense regions of vacuum pressure.
So they're more like
Yeah.
super concentrated pockets of this vacuum stuff.
Exactly. And this raises some interesting possibilities.
Like what?
Well, what if the vacuum pressure inside a black hole is so strong that it actually preserves information?
Even as the black hole evaporates.
Yeah, even
Then,
if-
so instead of information being lost forever, it's more like it's compressed and stored within the vacuum structure of the black hole.
that's one of the ideas they're proposing.
My mind is officially blown.
It's pretty mind-bending stuff.
Challenging everything I thought I knew
Yeah.
about space, gravity, even black holes.
It's a big shift.
And we're just getting started.
Oh yeah, there's a lot more to cover.
Well, I guess we have plenty more to dive into here with this framework.
Definitely.
Let's take a quick break, though, and we'll be right back to explore more of this SMF RVS dynamics. Welcome back, everyone. We're picking up our deep dive here into SMF RVS dynamics.
Yeah, this chapter keeps going.
Yeah.
It doesn't shy away from the tough questions.
Yeah, it really doesn't.
Tackling all those big puzzles in physics.
And it's trying to solve them all with the same idea.
It's all connected.
These subtle magnetic fields shaping the vacuum.
That's the key.
All right, so where do we go from here? What other mysteries are they trying to unravel?
They talk about neutrinos.
Okay.
You know, those tiny particles that are so hard to detect.
Mm-hmm.
And for a while, we thought they had no mass.
Right.
At all.
But then experiments showed they actually do have a tiny little bit of mass.
A little bit.
Which kind of messed things up.
Definitely threw a wrench in the works.
Yeah.
Yeah.
So how do you explain those tiny neutrino masses?
Well, that's where SMF RVS dynamics comes in.
Okay. How do they use the SMFs and the vacuum?
They suggest that those SMFs are actually shaping the vacuum in a way that gives neutrinos their tiny mass.
Interesting.
It's like the vacuum's providing some resistance.
Okay.
That's preventing them from being totally massless.
So instead of needing like a new particle to explain these masses,
you got it.
It's just the vacuum.
It's all about how the vacuum interacts with the particles.
Huh.
It's pretty elegant.
It is.
When you think about it.
Because it's like every time there's some mystery, they just point at the vacuum.
And all goes back to the vacuum.
And say it's those subtle magnetic fields.
That's the answer.
Well, it seems to be working for them.
It's pretty compelling.
Yeah. What's next?
Well, how about proton decay?
Proton decay.
Yeah. Do you remember that one?
Refresh my memory.
Okay, so some theories predict that protons should decay.
Okay.
But we've never actually seen it happen.
Right.
Which is a problem.
It is.
Yeah.
So how does SMF RVS dynamics deal with that?
They give us two possibilities.
Okay.
First, proton decay might be happening.
Yeah.
But it's so rare that we just haven't seen it yet.
So rare that we might never see it.
It's possible.
Like trying to find a needle in a haystack?
It's finding a grain of sand on a beach across the whole universe.
Wow.
Yeah.
It's a good analogy.
So the dynamic vacuum could be making it so rare that we just can't see it.
Okay. And the second possibility?
This one's even more interesting.
Okay.
They suggest that the structure of the vacuum itself might be preventing proton decay.
What? So the vacuum is like
a shield.
A cosmic shield.
Exactly.
Protecting protons from decay.
That's the idea.
That's crazy.
Certain configurations of the vacuum could be making protons basically indestructible.
Huh. So protons are only stable because of the vacuum.
Because the vacuum is keeping them that way.
Is keeping them that way.
It's a pretty radical concept.
It is. It is.
But it shows how this framework is making us rethink some of our most basic assumptions about the universe.
It really is.
It's not just tweaking existing theories. It's like a whole new way of understanding reality.
I'm starting to see why people are excited about this chapter.
It's big.
It's not just small solutions.
Yeah, right.
It's a whole new paradigm.
A whole new way of looking at things.
For physics.
For everything.
All right, so what else do they tackle with this?
How about
vacuum-centric?
Cosmic inflation.
Ah.
Remember that one?
Inflation.
You had the rapid expansion.
Right after the Big Bang.
Right.
Which explains why the universe looks so uniform.
Exactly.
On a large scale.
But the standard model doesn't explain what caused it.
Right. They just say it's this...
I say it's the inflating field.
Inflating field, but we don't know what that is.
Right, we don't know what that is.
So SMF RVS dynamics, does it have an answer for this too?
It does, and guess what?
Right.
No need for a separate inflating field.
Okay.
Instead, they say inflation was just a natural phase transition in the vacuum.
A phase transition?
Yeah, think about water changing states.
In the vacuum?
Yeah, from ice to water to vapor.
Okay.
It's all still water.
Right.
But the properties change.
Yeah, like ice is solid and water's liquid.
Exactly.
And steam's a gas.
Now imagine the vacuum doing something similar.
In the early universe.
Right at the very beginning.
Okay, how does that...
So they're suggesting
that
the vacuum in its initial state had super high pressure from those subtle magnetic fields.
Okay.
And this pressure caused the universe to expand rapidly.
So the vacuum itself was like a supercharged engine.
Like a cosmic engine driving that initial expansion.
And then
as the universe expanded and cooled, the The vacuum went to a lower pressure state.
Which led to.
And that's why we see the more gradual expansion today.
Wow. It's crazy how they tie all these things together.
All connected.
Neutrinos.
Yeah.
Proton decay. Inflation.
All through the vacuum.
It's like weaving a whole new...
It's like a new tapestry.
Yeah, a tapestry of the universe.
But we got to take another break.
Oh, okay.
We'll be back for the final part.
Sounds good.
Of our deep dive into SMF RVS dynamics.
Right.
Okay, we're back for the last part of our deep dive into this SMF RVS dynamics.
It really makes you think about empty space in a new way.
Yeah, it really does.
This chapter really changes how we think about the universe.
For sure.
Yeah.
It's like the vacuum is this conductor.
Yeah, like a conductor.
Of the cosmic orchestra.
Yeah, cosmic orchestra.
Shaping the music of reality.
That's a good one.
But before we get too carried away, there's still a lot to unpack here.
Where do we go next?
Yeah, where do we go from here?
Well, this chapter also talks about the quantum measurement problem. Quantum measurement.
Yeah, that whole idea in quantum mechanics.
Yeah.
Where particles exist in this superposition of states.
Right, like Schrodinger's cat.
Exactly.
Both alive and dead.
Yeah.
Until someone opens the box.
But the question is, what makes the wave function collapse when we measure it?
Right. Is it us?
Some say it's the observer.
Yeah.
Others say it's the measuring device.
It's a weird one.
It's a tough one.
So SMF RVS dynamics?
They have a different take.
What do they say?
Instead of those mysterious observers, they say the wave function collapse is driven by, you guessed it, the subtle magnetic fields.
And the vacuum. Okay,
Yeah.
But how do those tiny fields...
Well, think about it this way.
Okay.
When we make a measurement,
Yeah.
we're interacting with that quantum system.
Okay.
And that creates a disturbance in the vacuum.
Like a ripple.
Yeah, like a ripple in a pond.
So our measurement is like throwing a rock into the vacuum.
That's a good analogy.
Okay.
That rock changes the vacuum's pressure patterns.
So
it settles into a specific configuration.
That configuration
and that
determines the outcome.
Is the outcome we observe.
So it's not random chance.
Not really, no.
It's the vacuum responding to our interaction.
It's all about the vacuum.
It really is. Like the vacuum is the answer to everything.
It's a pretty unifying concept.
And so what else is there?
Well, they also talk about the origin of cosmic magnetic fields.
Oh,
those massive magnetic fields around galaxies and clusters.
Where did those come from?
That's a big question.
Yeah.
But with SMF RVS dynamics, it's related to those subtle magnetic fields again.
So those tiny fields become those massive...
Well, they act like seeds.
Seeds? Okay.
And through the vacuum's pressure gradients, they create these feedback loops.
Okay.
That generate those big magnetic fields over billions of years.
So those tiny ripples become huge waves.
That's a great way to put it.
In the cosmic ocean.
It shows how even small things can have a big impact.
Over a long time.
Over vast spans of time and space.
Okay, this is all super interesting, but I gotta be honest.
Yeah.
My brain is getting a little fried here.
I know, it's a lot to take in.
It is, it is.
But there's one more thing in this chapter.
Okay.
I think you'll find it interesting.
All right.
The fine structure constant.
The structure constant.
Remember that.
Vaguely.
It's a fundamental constant.
Right.
It's like 1 over 137.
Yeah, something like that.
And it determines the strength of the electromagnetic force.
Right. And if it was different?
If it was even a little bit different?
Yeah.
The universe would be totally different.
No stars, no atoms, no us.
Exactly.
So it's kind of a big deal.
It's pretty important.
Why is it that specific value, though?
That's the thing.
Yeah.
We don't really know.
So does SMF RVS dynamics have an answer?
They do.
What do they say?
They say it's an emergent property of the vacuum.
So the vacuum determines the value.
The vacuum pressure gradients.
Okay.
Shaped by those subtle magnetic fields.
It's like the vacuum is fine-tuning the universe.
It's a pretty amazing idea.
Yeah, for us too.
Shows how everything is connected.
So we've talked about all this stuff.
We've covered a lot.
Gravity, dark energy, black holes.
Neutrinos, proton decay.
Inflation, the Higgs.
Cosmic magnetic fields.
Even the fine structure constant.
It's all connected.
All because of the vacuum.
The vacuum is the key.
Is there anything else?
Well, the chapter ends with a challenge.
A challenge.
To physicists.
Okay.
To come up with new experiments.
To test this.
Yeah, to see the structure of the vacuum.
Like to actually see.
To see those pressure gradients.
Yeah, those subtle magnetic fields.
That would change everything.
It would be huge.
Like discovering the Higgs boson.
Or gravitational waves.
Exactly.
It'd be like seeing the universe's blueprints.
It would be incredible.
That's what makes this so exciting.
It's not just theory.
Yeah, it's inspiring new research.
Pushing the boundaries of science.
Well, this has definitely left us with more questions than answers.
It always does.
But that's what keeps us going.
It's all about exploring.
This chapter is like a call to action.
To look at the vacuum in a new way.
Not as empty space.
As the most important thing in the universe.
It's a big shift.
It really is.
Maybe one day we'll see those magnetic fields.
Oh, no.
Shaping reality.
Maybe one day.
Until then, keep exploring.
Keep questioning.
Keep diving deep.
And thanks for listening.
Thanks, everyone.